Hey there, science fans! Today, we're diving into the amazing world of chemistry. We're going to explore the language of molecules. Get ready to unlock the secrets of molecular formulas, percentage composition, and chemical equations. Understanding these concepts is like having a superpower. You'll be able to decipher the composition of matter. You'll see how substances transform before your very eyes. So, buckle up, and let's embark on this exciting journey into the heart of chemistry. First up, let's talk about molecular formulas. Think of them as the names of molecules. They tell us exactly what atoms are in a molecule. They also tell us how many of each atom are present. Let's take water as an example. Its molecular formula is H2O. This means a water molecule has two hydrogen atoms, H2, and one oxygen atom, O. Pretty straightforward, right? Another example is glucose, the sugar that gives you energy. Its molecular formula is C6H12O6. That's 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. Molecular formulas are key to understanding the world around us. Now let's move on to percentage composition. This tells us the percentage of each element in a compound by mass. Understanding this concept is crucial for chemists and anyone interested in the molecular makeup of substances. It's like a recipe that tells you the proportion of each ingredient. Just as a chef needs to know the exact amount of each ingredient to create a dish, a chemist needs to know the percentage composition to understand a compound's properties. Let's stick with water, H2O, as our example. Water is a simple yet fascinating molecule that is essential for life. The atomic mass of hydrogen, H, is about 1 atomic mass unit, AMU, and oxygen, O, is about 16 AMU. These values are fundamental in calculating the percentage composition. A water molecule has a total mass of 18 AMU, 2 times 1 AMU, for hydrogen plus 16 AMU for oxygen. This total mass is the sum of the individual atomic masses of the elements that make up the molecule. To find the percentage of hydrogen in water, we divide the mass of hydrogen, 2 AMU, by the total mass of water, 18 AMU, and multiply by 100%. This calculation helps us understand the contribution of hydrogen to the overall mass of the water molecule. This gives us about 11.1%. This means that in any sample of water, approximately 11.1% of the mass comes from hydrogen. Similarly, the percentage of oxygen in water is about 88.9%. Oxygen, being heavier, makes up the majority of the mass in a water molecule. See, that wasn't so hard. Understanding these percentages can help in various scientific and industrial applications, from pharmaceuticals to environmental science. Percentage composition helps us understand the relative amounts of each element in a compound. This knowledge is fundamental in fields like chemistry, biology, and materials science, providing insights into the behavior and characteristics of different substances. Now let's talk about chemical reactions. These fascinating processes are at the heart of chemistry, and are responsible for the myriad of changes we observe in the world around us. From the rusting of iron to the digestion of food in our bodies, chemical reactions are constantly occurring, transforming substances into new forms. These are processes where substances change into new substances. During a chemical reaction, the atoms in the reactants are rearranged to form new products. This transformation involves breaking old bonds and forming new ones, which can release or absorb energy. Chemical equations are like the sentences that describe these reactions. They provide a concise way to represent the reactants and products involved, as well as the proportions in which they react. Understanding these equations is crucial for predicting the outcomes of chemical reactions. A simple example is the reaction between hydrogen and oxygen to form water. This reaction is fundamental to life as we know it, and it also serves as a great illustration of how chemical equations work. The chemical equation for this reaction is 2H2 plus O2 yields 2H2O. This equation tells us that 2 molecules of hydrogen gas react with 1 molecule of oxygen gas to produce 2 molecules of water. This equation tells us that 2 molecules of hydrogen react with 1 molecule of oxygen to produce 2 molecules of water. The balanced equation ensures that the same number of each type of atom is present on both sides of the equation, reflecting the conservation of mass. The arrow means yields or produces. It indicates the direction of the reaction, showing that the reactants on the left side are transformed into the products on the right side. Another example is the burning of methane, CH4, the main component of natural gas. This reaction is a type of combustion, which is a chemical process that releases energy in the form of heat and light. The chemical equation for this reaction is CH4 plus 2O2 yields CO2 plus 2H2O. This equation tells us that 1 molecule of methane reacts with 2 molecules of oxygen to produce 1 molecule of carbon dioxide and 2 molecules of water. This equation tells us that 1 molecule of methane reacts with 2 molecules of oxygen to produce 1 molecule of carbon dioxide and 2 molecules of water. Combustion reactions like this are essential for energy production in many industrial processes and everyday activities. Chemical equations are essential for understanding and predicting chemical reactions. They allow scientists to communicate complex chemical processes in a clear and standardized way, facilitating research, development, and education in the field of chemistry. Section 5. Physical versus chemical changes, the heart of chemistry. In the world of chemistry, it's crucial to distinguish between physical and chemical changes. Physical changes are like changing your clothes. The substance remains the same. Think about melting ice. Ice is just water in a solid form. Melting is a physical change. Chemical changes, on the other hand, are like baking a cake. You're creating something entirely new. When you bake a cake, the ingredients react chemically and change permanently. Burning wood is a chemical change. You can't get the wood back after it burns. Chemical changes involve the breaking and forming of chemical bonds, leading to new substances with different properties. Section 6. Decoding chemical reactions, a world of transformations. Chemical reactions are incredibly diverse. They are the processes that allow substances to transform into new materials, often with remarkable changes in properties and energy. These reactions are the foundation of chemistry and are essential to understanding the natural world. Let's explore a few common types, each with its unique characteristics and significance in both nature and industry. First, we have combination reactions. These occur when two or more substances combine to form a single, more complex product. Two or more substances combine to form a single product. This type of reaction is fundamental in creating compounds that are more stable or useful than the individual reactants. Think of rust forming on iron. This is a classic example of a combination reaction where iron reacts with oxygen to form iron oxide. Next, decomposition reactions. A single compound breaks down into two or more simpler substances. These reactions are crucial in processes like digestion and recycling materials. Electrolysis of water is a great example. Here, water decomposes into hydrogen and oxygen gases when an electric current is passed through it. Then, displacement reactions. One element replaces another element in a compound. This type of reaction is common in metallurgy and the extraction of metals. Imagine dipping a zinc strip into a copper sulfate solution. The zinc displaces the copper, forming zinc sulfate and copper metal. Following that, double displacement reactions. Following that, double displacement reactions. These occur when parts of two compounds swap places to form two new compounds. Two compounds exchange ions to form two new compounds. Think about mixing a solution of silver nitrate and sodium chloride. The result is the formation of silver chloride and sodium nitrate. Finally, redox reactions. These involve the transfer of electrons between species, which is fundamental to processes like respiration and combustion. The reaction of magnesium with oxygen is a classic example. When magnesium burns in oxygen, it forms magnesium oxide, releasing a bright light and heat. Understanding these types of reactions helps us make sense of the countless chemical transformations happening around us. From the rusting of iron to the digestion of food, chemical reactions are at the heart of the processes that sustain life and drive technological advancements. Section 7. Beyond the equation, unveiling hidden details. While chemical equations are powerful tools, they don't tell the whole story. They don't show us the reaction conditions, such as temperature or pressure. To overcome these limitations, we use additional tools. Reaction mechanisms, for instance, provide a step-by-step account of how a reaction occurs. Thermochemical equations tell us about the heat changes associated with a reaction. Understanding these aspects is crucial for a complete grasp of chemical reactions. Section 8. Importance and applications. The power of chemical knowledge. The concepts we've discussed are fundamental to our understanding of the world. They have countless applications in various fields. In medicine, they help us develop new drugs and therapies. In agriculture, they guide us in producing fertilizers and pesticides. In environmental science, they help us monitor and protect our planet. The list is endless. By grasping the language of molecules, we gain the power to solve real-world problems and make informed decisions. Section 9. Conclusion: Chemistry, a Universe of Wonder. Congratulations, chemistry explorers. You've journeyed through the fascinating world of molecular formulas, percentage composition, and chemical equations. You've learned how to decipher the language of molecules. Remember, chemistry is everywhere. It's in the air you breathe, the food you eat, and even in you. So, keep asking questions, stay curious, and never stop exploring the wonders of chemistry.